get started. Lecture 21. It was something like that.
Lecture 21.
I don't want to spend a whole lot of time on this 4 to 4.6, but mostly application sections. Applications of the Hahn-Banach theorem. And I don't want to spend a long time. I want to get to the next main theorem, which seems to be a little bit more interesting, the uniform boundedness theorem, which is in 4.7. That's pretty meaty. Okay? And get into some more of the applications. So I'm going to spend some time and finish up 4.4. But there aren't even any problems on it. So it's more like, how does the Hahn-Banach theorem get applied? So we need that for our application. In other words, we still are focused in some sense on the Hahn-Banach theorem. I probably shouldn't have spent as much time as I did on proving the Hahn-Banach theorem. Well, we could have taken it as a shortcut. It's kind of important, but yeah, so I guess we can't get away from it. Here we go. So let's review the theorem that we're trying to get. Okay, so let's talk about bounded variation. Are there questions before we go on about anything right now? The syllabus has been updated. There are new problem sets. And I just want to get through these things.
We're all caught up on the notes. We don't have any.
There's some more notes here. I'm sorry about that. Yeah, sure. And some homework solutions. Okay. Take these. Okay, I think that should be about it. Okay. I was going through these notes and I noticed a bunch of typos, so I was hopefully corrected them. You'll see some ink writing on the notes. Okay, so I'm going to start roughly at the bottom, well, roughly on page 3 of these notes. Though I'm going to recall the definition of a step function. So, and I kind of went through the concept of Riemann-Stieltjes integral last time. We're going to have to review that as we go because I don't want to recover the whole thing. All right, so define the characteristic function chi sub t of s equal to 1 or 0 less than or equal to s less than or equal to t, and 0 t less than s less than or equal to 1. So for each t, I get a function, and I'm just working on the unit interval here. Instead of the interval a, b, I've mentioned that in the course of last time. So here's the independent variable is going to be s, and t is going to be a parameter. I'm just saying the function is 1 until t. Okay? And then it's 0 after t. So this is the point t on the s-axis. So this is chi sub t. He calls it x sub t, but I'm calling it chi sub t. That's more traditional. A characteristic function of an interval. Characteristic function of an interval. The interval is 0t in this case, of interval 0t, of the interval 0t. Okay? Sometimes called the indicator function. It has two names. The chi from characteristic, the Greek chi, and the indicator function is another terminology used. So you have that function. Now, why is that important? Well, why is that important is because if I use that function as a function of bounded variation, okay, that is a function of bounded variation. Its variation is just 1, the height, difference in the heights here, okay? Then integral x of s d chi t, okay, that makes sense, of s, okay, 0 to 1. What is that? That gives you what? That gives you, if x is a continuous function, that's just going to give you, well, it gives you negative x of t, I guess, in this case. Is that right? The difference is negative 1. So maybe I made a mistake here. No. So what is that? Well, that's negative x of t. I guess that's what it is. Okay? So t is fixed in that case. Is that right? If I do this, what is this? This is summation. Well, I'm trying to make this good. J goes from 0 to n, x of tj minus times chi sub t of tj minus chi sub t of tj minus 1. Okay? And then the limit of that as the gap with the partition p sub n, and tj's are the partition pn equals t0 less than t1 less than blah 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 less than tn equal to 1. This is 0 equal. This is what the partition is. So if I take the actual Riemann, the Riemann-Stieltjes integral, remember it's x dw. Well, this is my w now. Chi t is my w. So if I take tj minus chi sub t at tj minus 1, all right. Now focus on the case where the tj minus 1 and the tj overlap the t. So if I put the tj minus 1 here and the tj here, okay, then I'm getting chi at tj is 0. Chi at tj minus 1 is 1. All right, so I'm getting 0 minus 1 there. And I'm getting x of t, j. All right. So I'm simply getting x evaluated here, and then tj minus 1 is going to and tj are going to converge to t. If I pick just the tj as the gap of the partition goes to 0, and I pick the j and the j minus 1 so that they just overlap the t. So this is simply equal to the limit negative x of tj as the a to the partition which goes to 0, which is equal to negative x of t. Okay. So there's a particular case of a very simple function of boundary variation that evaluates the function at a point, except for the minus sign. Okay. Okay. So I think I might have a mistake in the notes there too. Okay. So where I wrote it down. Now, what I want to do is introduce then the step function. I also had a step function, z of s equals a step function. It looks like this. It's going to be of the form bj chi sub tj of s minus chi sub tj minus 1 of s. J goes from 1 to n. So I'll just go ahead and take the same partition that I have down here and define this thingamajig. What does that look like? That has a graph which, let's see, if I take chi, let's say just focus on j equal to 1. Chi t sub 1 minus chi t sub 0. What's that? Chi t sub 1 of s minus chi t sub 0 of s. Well, the one function is 1 on 0 to t1, and then 0 else. And the other function, actually, chi sub t0, that's, I'm just looking at the interval from 0 to 0 in that case. Remember, this stands for the interval 0 to t1. Maybe this is better to write it, 0 to t0, to write it with the actual interval as a subscript. It might be easier to see what I'm talking about. Okay. Let's take the whole interval as a subscript. It's the indicator function of that interval. All right. Chi p or equals chi sub interval 0 to t when I need more emphasis. Okay? Okay, so one is the interval from 0 to t1, the other one is the interval from 0 to t0, which is 0 to 0. So the other one is just a function which is 1 at one point and 0 otherwise. Okay? So this is this is the difference of those. So what you're getting is the function which is 0 at the left-hand endpoint. Excuse me, well, chi sub t0. Okay, so then I'm getting this function which is, okay. The whole thing it's 0, then when I subtract. So 0 here, and then it's going to be a height b1 on the first interval up to t1. Then this is going to be z of s. Then it's going to be b2 on the next interval, however long that is, up to t2, and then it's going to be some other value. b3 on the next interval up to t3 and so on. So that's what the step function is going to look like. It's actually 0 here. Okay, if you look at it, because this difference is 0 at 0. The difference of the two characteristic functions. To subtract this gives you the function which is 0 at this point, and then it's 1 up to this point. Okay, t1, and then it's 0 afterwards. 1. This difference minus this equals this. Okay. All right, and so you can do that on any, difference of any of the two chi's. All right, and then you just shift this thing over. Okay, so the difference of chi t2 minus chi t1 is a function which is 1 on this interval and 0 everywhere else. Okay, so therefore I haven't shown the 0 everywhere else part. All right, the only 0 I've got in here is at 0. So if I take a linear combination of these things, and there's no overlapping, and I get this business. Okay, finally there's the last one, bn. Height bn at 1. Okay. So that's what the thing looks like. And now we'll restate the theorem. Okay? So you can make this function, and so what's a theorem? The theorem is let f be a bounded linear function on C01. This is 4.4-1. Let f be a bounded linear function functional on C01. We looked at some examples last week or a week before last. Whenever we were started on this. Bounded linear function on C01, then f may be represented as f of x equals interval 0 to 1 x of t dw of t for some function of bounded variation w in the functions of bounded variation on 0, 1. And the norm of f, which is already given by giving f, because f is a bounded linear functional, is equal to the variation norm of w. Total variation, so-called. It's not the variation norm, but the total variation of w, so-called. The reason why they call it the total variation is that you can talk about the variation up to a certain point. In other words, this was the supremum. 0 less than equals t0 less than t1, less than so on, less than tn equals to 1 of the sum w tj minus w tj minus 1. That's what the variation is. J goes from 1 to n. The supremum, in other words, all the ups and downs that the function could make, the supremum. If I take, this is so-called total variation because I can talk about just a variation up to an arbitrary endpoint like t. And then obviously that variation increases. All right, so you'll see this written, talk about it as the total variation. So this just means bounded variation. Okay? That means this norm is finite. Okay? The norm of f was already assumed to be finite. We had a bounded linear functional. Okay? So bounded linear functional given, it can be represented this way. So this is, remember in the Riesz representation we had represented all the bounded linear functions in terms of the inner product. Well, this is kind of an analog then for a non-Hilbert space. Okay? So what's the proof? We're going to apply the Hahn-Banach theorem. Okay? Which one? The 4.3-2, which tells me if I have a bounded linear functional on some subspace of a normed space, then I can extend that bounded linear functional having the same exact norm to the whole space. Okay. So I'll apply 4.3.2 as follows. Let's get through this little theorem. I think it'll be worth it. So the whole thing is to see how this application comes in. 4.3-2. I'm not going to write down 4.3-2. What I'm going to do is you can, because you have your books there, you can look that up. Okay? It's one of the three versions. This one, this X 4.3-2 and 4.3-3 are the ones we're going to use. Okay, always. Pretty much. And then there's another corollary. So what it tells me, okay, what I'm going to do is let X be I need a norm space in which I can do some extending. I've already got a bounded linear function on C01, so this is going to be my subspace now. This is going to be my Z. Okay? So now I need a space in which Z is a subspace. Okay? That means I need a norm and a space so that the norm when applied to C01 is just the usual max norm. Alright? In other words, I can't go changing the norm. Okay? Of C01. That's already given. It's the max norm. Okay? X is the function. The continuous function. Continuous function, and this norm is the max norm, so I need to come up with, and that is X equals the bounded functions on 0, 1 with the norm X equals the supremum T belongs to 0, 1. So for example, this Z function here, this is not continuous, but it's an element of B0, 1. It's a bounded function. Just a step function. Okay? In other words, the graph lies between two horizontal lines. Okay? Right? So it's just the maximum of the B's there. Absolute max. So here, but in general, I have to talk about the sup. X of T. Okay? So that sup may not be attained, but that is a norm. Okay? Obviously, if you take a difference of two bounded functions, you get a bounded function. And if you take the sup of the difference, if that's 0, then of course the difference of the functions is 0. You can't get the sup to be 0 unless the functions are identical in that difference. Okay? Right? So that is a good norm. In other words, if you take a difference of two functions, all right, then I have a function. I take the sup and find the sup is 0. Well, the sup is 0 means the function is 0. Okay? In this case. Right? So there's no problem with that being a norm. And obviously, if I apply to a continuous function, I just get the maximum because we know that we have the extreme value theorem. If I have a continuous function on a compact set, then it attains its maximum. Okay? So Z equals C01 is therefore a subspace of X. Okay? That's all I need. Now, so what am I going to get then? Okay, so I gave myself an f, so therefore there exists an f tilde, a bilinear functional on the B space, on B01, with the norm of this f tilde on B01 equal to the norm of f relative to C01. Okay? So its norm is the same. I can extend the function linearly, and it has the same norm, same exact norm. That's the Hahn-Banach theorem. Okay, now why is that going to be any good? Well, I'm going to use this f tilde to represent x. To define w. Now, I thought I had a clever way of doing this, but I wrote down a formula wrong. Okay, looks like I got a minus sign wrong. So I'm going to leave this definition here. We know what this step function looks like. Now we have a pretty good picture in our mind's eye. And so now I'm going to define. This is the proof. I'm just going to continue this. This is going to be late for later consumption. Define w of t. I'm just going to go ahead and define what my w is supposed to be. It's going to be f tilde of chi sub t. Chi sub t is an indicator function of s. And I think I got that right. Let's see. But we'll just check through the proof. It seems like I'm missing a minus sign somewhere in my mind, but maybe that's because I've got the idea wrong. Okay, that looks okay. So, and this is for t greater than 0, for 0 less than t less than or equal to 1, and also I'm going to define w of 0 equal to 0. Okay. At t equal to 0, that's the way I'm going to define it. Okay. This is not quite the 0 function at t equal to 0. It's got one point in it. So it's not going to make any difference, I don't think, in the calculation. So we'll just do this to see what happens. Okay? So the claim is this is going to work. Claim this works. Okay? In other words, this is the representation with this w. Now, why should that work? Why should that work? I mean, that's what I was going to try to show, is why that should work. It should work because, let's see, I want something. Well, let's see how. Maybe we'll see by the end why it should work. Let me see. Let me see. Yeah. Okay. Well, I think it's going to work. So let me try it. Okay. So what I need to do is there's only one little complication. Otherwise, the step function thing does the whole thing, and that is the case of complex coefficients. It makes it a bit of a burden on the notation. So I have to consider complex coefficients. So what I need to do is first thing I'm going to do is I'm going to calculate the variation. Summation w of tj minus w tj minus 1. I want to estimate this variation. J goes from 1 to n. And I have to take into account the fact that these w's are complex in general. Okay, so this is the bounded functions. Everything's complex. If I do the real case, it's a little bit simpler, but I might as well do the complex case just to get the whole thing. Okay, so you won't see there's really any complication. What I'm going to do is first I'm going to write this. J goes from 1 to n as simply f tilde of chi t minus f tilde chi tj minus f tilde of chi tj minus 1. Okay, absolute value. All right. Now what I want to do, except that the first term is special because, so I have to write it this way, equals f tilde of chi tj, chi t1. Okay. Minus 0 if you want to put in the minus 0 because w of 0 is 0. Okay. Okay. Now what am I going to do? What am I going to do? I'm going to... this proof is a little bit nasty. What I need to do is plus. This is a plus sign. I need to calculate those absolute values, and what I want to do is I want to write this basically as f tilde of a step function. Is what this is going to come out as. Okay, a certain step function. F tilde of a certain step function. Let's see how that works out. You can see the step here. This is f tilde. The difference of f tilde is f tilde of a difference because f tilde is a linear functional. So this is f tilde of a difference. Chi tj minus chi tj minus 1. Okay. And then absolute value sign here. Okay. Now how do I get rid of the absolute value sign? Okay. Well, it's either plus. If it was a real case, it's either plus or minus that, right? So then I could, so then I could actually bring the plus or minus inside f tilde. Okay, and I'm going to do the same exact thing, only without plus or minus. I have to use complex numbers of modulus 1. Okay. So what I'm going to write is any complex number zeta equals the modulus of zeta times e of zeta, where e of zeta is simply e to the minus I theta, where theta is the argument of zeta, okay? For zeta equal e to the I theta, okay? So this is e to the, so this is plus I theta, okay? And so what I'm going to get is that the magnitude of any complex number is zeta, the complex conjugate of this e of zeta, okay, which is the e to the minus I theta. So there's a complex number of modulus 1. So that's like saying that a real number is its absolute value times plus or minus 1. Okay, there's just a plus or minus 1 factor in there. So what I'm going to do is now write an absolute value of f tilde of chi t.
Modulus 1, right?
Modulus 1, yeah. Of this thing, I'm simply going to write as f tilde of, I'm just going to write it as this thing. This is the box I'm going to use. Okay. F tilde of the difference without any absolute value signs times e of the same mess. Okay. E of f tilde of chi tj minus chi tj minus 1. Okay, so I'm just writing the whole mess down again, only putting an e on the outside of it. Okay, and this expression here is with a conjugate sign. Okay, all right. So this whole mess here with this conjugate sign is a complex number of modulus 1. It's akin to the plus or minus sign. All right. So here, when I drew the picture of the step function, I used real coefficients to draw a picture. But you can imagine them as complex coefficients as well. Okay? So I'm going to think of these as complex coefficients. And now what I can do is I can bring that on the inside. That's just a complex number. I can pass it across to F tilde. Okay? That's just a complex number. All right? It's not a function. Well, it's a function of S. But for each fixed S is this complex number. Okay? So I can bring it inside if I want. Okay? And so what I'm getting is I'm getting then that this whole business, this Vn, is therefore Vn is equal to F tilde of a step function, okay, of a certain step function, summation beta j. Okay, let's call this the beta j then. Okay. Times the chi tj of S minus chi tj minus 1 of S. Okay. Okay, so that's the business. I know it looks like cheating. Okay. But I can actually, this is a number. Okay, for each S it's a different number, and then this is F tilde applied to some function. Okay, so this is my F tilde is this mapping that takes a function, all right, and turns it into a complex number. And here's a complex number on the outside. Okay, so I can pull that complex number across by linearity. All right, so I'm getting this, where this is my beta j. Okay, so I have that. So I have some weird complex valued function here on the inside, F tilde applied to it. And it's a bounded function. It's not a continuous function. Okay, but F tilde was on all of the bounded functions. Okay? And so this is less than or equal to the norm of F tilde, okay, which was equal to the norm of F, okay, times what? Times the norm of the step function. Times the norm of the step function. So I'm just throwing this term away because I don't want to rewrite it all the way time separate at this point. Okay, because the first term is beta 1 times chi t1. All right, I'm just pretending it's this way instead. I guess I can go j equals 2 to n. All right, I'll put it in there if you want. Beta 1 chi t1 of S. Okay, plus this. Okay, so times the norm of this business plus summation j goes from 2 to n chi tj minus chi tj minus 1 of S. It was a little bit hard to see what he was doing, so I wrote it all out. Beta j here. Okay. Now, what is the norm of this little thingamajig here? Well, these are complex coefficients of modulus 1 hitting these steps. Okay, so you just have a bunch of steps. Each step of height in the complex, in terms of is of magnitude 1. Okay. So therefore, this is simply 1. This last thing, this is just the number 1. If you want, you can say this is the max of the beta j in modulus, but all the beta j's are equal to 1 in modulus. So this is exactly 1 in this computation. Equals the max of 1 equals 1. Max of 1 equals 1. Okay. That's the bounded. This is the soup norm here. This is the B01 norm. So this is equal, therefore, to the norm of f. This upper bound is equal to the norm of f. Okay, therefore, what we've shown is that the variation norm of w is less than or equal to the norm of f. Okay, so that's good. Because I'm going to take n to infinity, and I have this constant upper bound. I'll let n go to infinity, and so I'll take the sup of all this business for my Vn. All right? Therefore, okay, let's put it this way. Therefore, variation of W equals the sup over all possible partitions Pn of Vn is thus equal to this. Okay? Okay. All right, so let's finish this thing now. All right, let's now calculate and show that that my f of x is actually equal to the Riemann-Stieltjes integral. Okay. So now what I'm going to do, I'm going to take a specific z sub n. So what I'm going to do is I'm going to basically construct a step function that looks a lot like x. So now define z sub n of s equal to x of 0 times chi sub t1 of s plus summation x of tj minus 1. I guess I'm going to take the left-hand endpoint of the interval. Now, if you'll notice in the book that when he defines the Riemann integral, Riemann-Stieltjes integral, he took the right-hand endpoint of the interval. It doesn't matter which one I take. I can take any point in the interval, tj minus 1 to tj, and I get the consistent definition. You can see in my notes. I changed it a little bit from the book. Okay? So I don't know if he didn't revise the section or whatever. It's a pretty clean book, but I could take any t in the interval tj minus 1 to tj and get the limit here. Okay, so this is my step function I'm going to take now. J goes from 2 to n. And this is an approximation of x, obviously. Okay, in the B01. This approximates. So what I have is that Zn minus x. Let's see, just check that in B01. All right. What is this norm? This is the sup. This is the sup. J goes from 1 to n of xt minus xtj minus 1. This is t belongs to tj minus 1 to tj. This is actually what it comes down to. This is the t is free from the x, okay, and the tj minus 1 from the zn, because this is what the height of this function is x tj minus 1 on the whole interval tj minus 1 to tj. All right, so it's just this height from the zn and this height from all the other t's, where t belongs to this interval. Now, is that supremum finite? Well, yes, because in fact, this is the maximum variation over a small interval of a continuous function is small. Okay, a continuous function on a compact interval is uniformly continuous. Remember that good stuff? You probably don't remember very well, but that's something that you get. That's what you actually needed when you actually do the Riemann integral of a continuous function in Calc 1. You need to know that the function is uniformly continuous. Remember in Calc 1 you take a function, a continuous function on a closed interval or what have you, 0, 1 let's say. All right, this is my f, and I just want to integrate integral f of x dx, right? What I do is I took a Riemann sum, so I get all these rectangles and blah, blah, blah. Okay. You've seen it a million times. But then when you actually estimate the Riemann sum, the error in the Riemann sum, what you get is you have to take the maximum of the function of the difference of the function you have to take f of x minus f of xj star or whatever, okay, and take the maximum of that, okay, then multiply by delta x, the maximum of the length of the interval, so which is the eta of the partition, okay, all right, this is on j, then that was the error, okay, you've incurred in estimating the area under the curve with the Riemann sum, so just intuitively thinking in terms of the area already being defined, okay. So this is the error, and so you had to know that this goes to 0 when the eta. No. This is the sum, this is the length of the interval. I'm sorry, because you're taking the total error. So this is times the length of the interval b minus a or whatever. Okay. So just in the ordinary theory in Calc 1, you need this. I need that the function, a continuous function, is uniformly continuous. That is, x of t continuous on 0, 1, which is a compact interval. Okay, implies that for every epsilon greater than 0, there exists a delta greater than 0, so that if x2 minus x1 less than delta, then f of x2 minus f of x1, x of t2 minus t1, I got to go back to independent variable land, then x of t2 minus x of t1 less than epsilon. So in other words, the t1 and t2 are not, there's not one of the t's isn't fixed, okay? They're free, all right? So therefore, the supremum is going to 0 as the length of as the gap of the partition goes to 0, right? For Zn minus x, therefore, in norm in B01 goes to 0 as the length, as the gap of the partition goes to 0. Okay. So as I take this delta, the gap of the partition is the delta. Okay? The max delta. Okay? So this is in other words, give me epsilon equals 1 over n, or any big number. All right. Give me your epsilon. I want to make this smaller than epsilon. I can make this smaller than epsilon by taking there exists a delta, so that if the t and the tj minus 1 less than delta, the tj minus 1 less than delta, then this supremum is less than epsilon. Any more comments necessary on this? You follow that? Kind of? Just this uniform continuity. Okay, sorry. I wasn't planning to spend a lot of time on that. But that's one of the things people don't remember about. Okay, so that's going to 0. So that's a good approximation of x in the bounded functions. So there's the step function approximating the continuous function. Okay. Then what do I actually get then? If I actually take f tilde of that thing. What's f tilde of Zn? That is equal to x of 0, w of t1, because I'm just going to, these are just the coefficients, I'm going to apply f tilde to each of these. And what is f tilde applied to this chi t? Well, that was by definition w of t. That's the definition of w of t. Plus summation x tj minus 1. The f tilde applied here. I'm using linearity. This is just a fixed number. Again, the complex number. F tilde, a difference of two functions. Well, f tilde is linear, so f tilde of a difference is a difference of f tildes. F tilde at this one is w of tj. F tilde at this one is w of tj minus 1. So this is simply the Riemann-Stieltjes sum for the integral. Oh, that looks good then. If that's the Riemann-Stieltjes sum, we know where that goes. This is simply the Riemann-Stieltjes sum for the integral x of t dw of t, 0 to 1. Therefore, I'm just about done. Okay. Because, therefore, then this goes to, as n goes to infinity, goes to, and the eta, when I take the partition going to 0, okay, we're simply going to take, we could just take any partition we want, all right, whose gap goes to 0, all right? And so I didn't say what partition I was using here, but I'm just going to take one where the gap goes to 0. So I could take the uniform partition in particular, if I wanted to. This goes to the integral 0 to 1, x of t dw of t. Okay? Because that is the Riemann-Stieltjes sum. Okay? And that's a theory of the Riemann integral. All right, now, what else? I already gave you that Zn minus x is going to 0, though. Okay? So therefore, what I have is that but f tilde of Zn minus f tilde of x. Okay, that makes sense. Because f tilde applied to a step function or to a continuous function is just it's good on both of them, right? So this is equal to f tilde of Zn minus x. Okay. Let's put absolute value. Okay. Absolute value, which is less or equal to the norm of f tilde, which is the norm of f, times the norm of Zn minus x, which goes to 0 as n goes to infinity. Okay. Or the norm of the partition goes to 0. Okay? So, that's going to 0. This is a fixed number. Therefore, I've identified this number as that number. Okay? Therefore, f tilde of Zn goes to f tilde of x. Alright? If n goes to infinity. Well, okay, you can't have two different limits. This is just a sequence of complex numbers. Okay, it goes to this complex number. The Riemann-Stieltjes integral goes to this complex number, f tilde of x, and therefore they're equal. Therefore, f tilde of x, which is simply f of x by the extension, okay, is equal to integral 0 to 1 x of t dw of t. Okay. And that's the representation. Finally, you want to show that the norm of f is less than or equal to the variation of w. We already saw the other inequality, but that follows immediately from the definition of the Riemann-Stieltjes integral. The norm of f, okay, which is the same as the norm of f tilde, okay, this was equal, well, in absolute, let's put f of x in absolute value. Therefore, absolute value f of x, less or equal to integral absolute value x of t dw of t, whoops. But that's automatically, we have the variation norm inequality. This is always less or equal to the norm of x, the max norm or sup norm, times the variation norm of w. That followed directly from the definition of the Riemann-Stieltjes integral. And therefore, the norm of f is less or equal to the variation of w. Okay. Because norm inequality. So, therefore, we got the final statement. Hence, the norm of f is equal to the variation of w because you already showed the reverse inequality. Okay, seemed like magic. Okay. it seems like it came down to that minus x of t evaluation. In other words, that's what I tried to explain. In other words, I have f of x equals to integral x of t dw of t. Okay, and I'm supposed to make, I think that's what I wanted. Maybe I wanted to write this as an integration by parts formula. This was supposed to be, yeah. I could write this as, if I could think of writing it this way, maybe I can write it like this. And so what should that mean? That means that well, there's some constant here. Is this how I want it? So this is off the record. Turn off the phone. So this was supposed to be, and I had that the integral of x of s d chi t of s was equal to minus x of t 0 to 1. So is that going to help me any? I thought I was going to bring that in. So somehow I wanted to apply f of, so I want to get, how am I going to get w of t? How am I going to get w of t? Let's see. So I don't know. All these equations, I still don't see how, they got how to unravel it. I have to look at it a little bit more. Okay, so before they come up with that definition. Obviously it works. Okay. The f tilde of chi of t, w of t equals f tilde of chi sub t. That worked. And the reason it worked, it seemed to be, was that we were able to represent x back in terms of the step function in terms of chi of t. I don't know, it kind of fell out in the wash. I don't know. I guess you have to stare at it a little bit more. Let's see. How did it come out? So I wanted to look at this. If you could obviously make this, I had that basically x sort of looks like summation xtj minus 1 chi tj minus chi tj minus 1. That basically is what x is. Okay. And so, okay, well then I guess that makes sense. Then I want to have f of x, therefore, this is the easier way to do it, is f of this, which would be f of that. Okay? And so, so now I need, I need this to be, and then I want to make this a Riemann-Stieltjes integral, so I want this to be w of t minus w of t, tj minus w of tj minus 1. That's true if this is true. Okay? So I think that's the easier way to see it. I think the other way I was trying to show by doing the integral is another way to see it. But I got that minus sign in there, so I have to go to somehow the integration by parts formula in order to show it that way. It's a little more complicated. This is the guts of the proof, basically. You say x is basically the thing without the f. Okay? That's the idea. So just write step functions. So a whole lecture on step functions. Jeez. Okay, let's do one more application before we are done for the day. Maybe we can get one more application in. There's a little thing in section 4.5 called the adjoint operator. I'm not going to spend much time on it. There's a Hilbert adjoint operator, and there's a general adjoint operator. And I'm more interested in 4.6 than I am in 4.5 in terms of the application. There's some interest. So I'll discuss 4.6 next time, and I may have to finish up a little bit with 4.5. But I'm going to mainly just kind of give 4.5 just a little bit of interest because you probably need to know that adjoint operator is there. And it's another application of the Hahn-Banach theorem, but we're not going to spend any time with it. As you recall, the Hilbert adjoint operator T star corresponded to complex transpose, right? You take the complex conjugate of a matrix and then you take the transpose. The general adjoint, when you're working with normed spaces, is simply corresponds to take the transpose and no complex conjugate. Okay, so it's a different operation.
Yeah, that's been causing me some head scratching too, because in a lot of functional analysis books they distinguish between self-adjointness and Hermitian operators. Couldn't figure out why.
Okay.
So that must be it.
Yeah, that must be it.
Yeah, that's been bugging me for a while.
Okay. So this is the adjoint operator.
I haven't seen it before. Is it?
Well, I don't know. We're not going to use it much, but I'll just mention about it. We'll just generally mention the structure. If X and Y are norm spaces, now, so I don't have to be working with Hilbert spaces, right? Are norm spaces. So it sort of depends where you're working. If these are norm spaces, and T is a bounded linear operator. Okay, then what you can do is talk about the dual spaces, right? Let G be in Y prime, the bounded linear functional on Y. Then what I'm going to get is by applying G to T of X, I'm going to get, this generates a bounded linear functional F belongs to X prime via the formula F of X is equal to G of T of X. I don't need the parentheses because you're not supposed to put parentheses after the T. Okay. F G of Tx. Okay. X is an element of X. All right. G is a linear functional on Y. Okay. So I'm going to go from X to Y with the operator T. It gives me a vector in Y, and then I'm going to apply G to it, and that's going to give me a linear function. Obviously, this is linear. It's a composition of linear mappings. It's linear. Okay? And it's bounded. The norm of F is what? Is equal to the supremum of G of Tx X unequal to 0 divided by the norm of X, okay, which is less than or equal to what? G is itself linear functional, so this is less than or equal to the norm of G times the norm of Tx divided by X, supremum X unequal to 0, which is just G times the norm of T. Okay. So F is a bounded linear functional. Okay. So that's a bounded linear functional. Now, what you're interested though is in the operator. The adjoint operator is the thing that maps G to the F. Okay, so what about it? The adjoint operator is this T super little x. Well, it's not an x, it's like a little times sign. It's like some kind of placeholder. It's like the asterisk without one of the star rays. Okay, whatever. 4x4 asterisk. I don't know. But anyway. Okay. Tx from y prime to x prime. Okay, given by G goes to F, okay, where F equals G, F, where F of X equals G of T of X. Okay, that's the formula. Okay, so that's the adjoint operator. Remember, Y prime and X prime are norm spaces. In fact, they're Banach spaces. Okay, and that's the mapping. So you're mapping actually from the dual of the Y to the dual of X. Okay, and then what you know is the following. What do you know? What's the norm of Tx? Okay, will therefore be the supremum over all G unequal to 0 of Txg, which is the F, divided by the norm of G. But the norm of Txg, okay, is the norm of the F, which we just showed, which is less than or equal, therefore, to the supremum G unequal to 0 of the norm of the F divided by the norm of the G. The norm of the F, we said, though, is at most GT. So this is less than or equal to norm of T divided by norm of G, G unequal to 0. So the G's cancel and you just get norm of T. So the norm of Tx is at most the norm of T. Okay, that's a lot of norm stuff. This is where that norm comes in handy. You just do everything mindlessly. Put norms on everything and just keep going. Okay? There's no designation of the norm on what space or anything like that. Okay? It becomes efficient. But basically, that's what we've learned how to do in the first 10 weeks. Okay. So, I mean, if you're a little nervous about everything, it's good. It's a good sign at this point. So, what you want to show, then, to use the Hahn-Banach theorem, one of these corollaries, to show that actually the norm of T super X is equal to the norm of T, or whatever you call this thing. Is the norms should be equal. In other words, show the reverse inequality, and that's going to be using. The reverse inequality. And actually, that I should be able to get through that so that we can be done with this. And then next time I can just show you the little bit of the matrix stuff. Okay? So let's get the theorem. There's another application of the Hahn-Banach theorem via which one? Theorem 433 this time, which you had to use in your homework. So hopefully you remember that one. 433. Remember, if X is 433, X is norm space, okay, and X0 unequal to 0 is an element of this norm space, then there exists a bounded linear functional with the norm equal to 1, and well, let's put it this way. There should be a G. Let's put it this way: G0. I'm going to apply this to Y actually. So and Y0 unequal to 0, Y0 and Y. Okay. Then there exists G0 and Y prime with G0 of norm 1 and G0 of Y0 equal to the norm of Y0. Okay? That's what the Hahn-Banach theorem 433 gives you. I'm using it on the space Y. Okay. Now, so what I'm going to do is take Y0 equal to T of X0 for some X0 unequal to 0. If Y0 turns out to be 0, then everything's going to come out in the wash. You can't get G0 of norm 1, but that's not going to matter when I get to the bottom. So pretend Y0 is unequal to 0 now. Okay? And then we get to apply this theorem. Okay? Then so you have this G0. So G0 of Y0, okay, is equal to G0 of T of X0. Let's just see what happens. That was my T sub X G0 at X0. In other words, my F of X0. Okay? And so, therefore, what you have is that Tx0 in norm, which is the norm of Y0. It seems like you just have to play around with this until you get the order right. Okay? This is equal to this G of Y0. This is equal to the G of Y0, G0 of Y0, because that was this property of the harmonic theorem here. Okay? G0, and then that's equal to this F of X0, or the Tx of G0, okay, equal to Tx of G0 at X0. This super little x is confusing, but okay. And then this was just in value, okay? And that's obviously therefore less than or equal to the norm of Tx G0 times the norm of X0. That was the original, that's just the norm of F times the norm of X0. Okay? And we already said what this thing was. We already did this whole thing. This was less than or equal to the norm of T super X, the norm of G0, and then the X0. We already did this. All I'm adding in here is the norm of X0, which was the denominator in the definition of the norm of F. Okay? So now it's not in the denominator because I'm doing the inequality. Now, but G0 has norm 1. So this is equal to T super X norm. This is 1 times the norm of X0. Therefore, what I've got is that I've got the T of X0 less or equal to this. And therefore, the norm of T is less or equal to the norm of T super X. There's a T super X here. There's a T here. Okay? So, the norm of T is less or equal to the norm of T super X. Now, there was no intuition involved here. Okay? This was just use it and see what happens. I guess after you work with this stuff for a while, you get some intuition. Okay? This is what you get. And so, done. Okay? So I get the norms are equal. Let's see, if Y0 was equal to 0, what would fall apart here? If Y0 was equal to 0, then I simply got, this was just 0. So that wasn't very interesting. Okay? I got 0 here, so that's always less than or equal to that. Okay? Okay. All right. Next time we'll talk about this adjoint in terms of matrix transpose. We'll go to the bottom of page 5, top of page 6 of these notes, and then we'll go on to application to reflexive spaces. Turns out that we're going to be able to talk about whether certain spaces can be reflexive or not. That is, their second dual equal to the original space, depending on whether the dual is separable or not. If the dual is not separable, then you can't get back to the original space by taking the second dual. Okay. So that was the case with L1 and L infinity. L1, the dual was L infinity. L infinity is not separable. L infinity is kind of this counterexample space. It's not separable. Therefore, the second dual, the dual of L infinity, which you already know is not L1, but it's kind of a hard problem, okay, is not L1. So in other words, L1 goes to L infinity for the dual space, and then if you would take the dual of L infinity, it's not L1 again, right? Because the L infinity is not separable. So that's coming. So that little application comes out in this next section, okay, that in order to be reflexive, in order for the space to be reflexive, the dual must be separable. Okay. So that'll come out That's kind of a nice application. Then we'll go on to the uniform boundedness theorem. That's a nice application. From section 4.7, I've assigned 3 problems that's non-trivial. Okay, there's the category theorem, which gives you the uniform boundedness theorem, and that's already just understanding the category theorem. That's harder than understanding partial ordered sets. So we need to understand the category theorem. That's going to be a bit of a difficulty. So we're going to spend a good day and a half on that section. All right. Thank you. So